Good morning, everybody. In today's lecture, we will discuss one of the very important topic of impact of jets. But before going to that, just recollect what we have discussed in the previous class. In the previous class, we discussed on series of vanes mounted on a wheel, and the wheel is rotating at a constant angular speed. And the jet is striking at the center of the vane. In such a case, what is the force? What is the work done? What is the efficiency? What are the conditions for maximum efficiency? How much maximum efficiency we can get if the vane is of semicircular shape? You all just recollect, if it is a semicircular vane, we get 100% efficiency. But that is only theoretical, because always there is friction loss, which reduces that efficiency. Exactly the same principle is being used in one of the turbines named as Pelton turbine. In Pelton turbine, the jet strikes at the center of the vane and then leaves at the edges. And there we get almost the hydraulic efficiency up to 95% plus. So that is the application of the previous case. Now in today's case, instead of the jet striking at the center, if it strikes at one of the ends, if the jet strikes at one of the ends of the vane and leaves at the other end, the vane is moving. At the same time, I will do for the most complicated case of an unsymmetrical vane. So in today's lecture, what we are going to do is how to determine the force exerted by the jet, the work done by the jet, the efficiency in case of a single vane moving, jet striking at one end and leaving the other end. Note that the vane is symmetrical. It's not that easy. In previous case, the jet is moving in X direction. The vane is also moving in X direction. Now what we are talking is the jet is striking at one end, that is basically in the inclined position, whereas the vane is moving in the X direction. In such a case, how you are going to calculate? In the previous case, both are moving in only in the X direction. The relative velocity is nothing but one minus the other. The maximum absolute velocity minus velocity of the vane is equal to the relative velocity, because it is all in X direction. But now the velocity is striking the jet velocity striking the vane is in the inclined position, whereas vane is moving in the horizontal position. So now what is the relative velocity? How to calculate that relative velocity? What is the principle behind it? These are the cases which we slowly unwind each and every point and try to understand the principle of it and try to derive the equation for the force, then work done, then efficiency. With this, I will take you to basically to the white. Jet striking an unsymmetrical moving curved vein tangentially at one of the tips. That means if I draw the figure, please see that. So this is the curved vein. So this is the direction of motion of the vein. The vein is moving. This is U. Now the thing is jet is striking here. This is V1. The jet is leaving here. So this is the case, and the vein is unsymmetrical. So jet is striking at an angle at V1 here, and the vein is leaving at U. This is in X direction. This is inclined position. So now if you want to calculate what is the effective velocity with which the jet strikes the vein, then naturally the only way to calculate the effective velocity is only by drawing the velocity triangles. Unless you draw the velocity triangles, you will not be able to calculate the effective velocity or relative velocity with which the jet strikes or leaves the vein, as the velocity of jet is in inclined position. Velocity of vein is in horizontal position. That is why to calculate the effective velocity, we need to draw the velocity triangles. So how to draw the velocity triangles at the inlet and at the outlet? If you understand this, the whole derivation is very simple and easy. So kindly understand how I am doing it. So this is how the vein is. Again, I am repeating it. Right? This is how the vein is moving. So now basically the jet is striking like this. This is what we call it as absolute velocity. So this is what I call it as, I name it by AB. AB is nothing but actually, if you take it, it represents the absolute velocity, right? Then if I represent on the same scale how the vein is moving, this is how the vein is moving. Actually, it is U only to represent this position as inlet and this position as outlet. I am writing all dimensions at inlet, all parameters at inlet with suffix 1 and at outlet with suffix 2. That is the only reason. Otherwise, U and U1 are same, right? Next. So what is the effective velocity? What is the relative velocity? So this will be the relative velocity. If I note it as C, so naturally this will be the relative velocity. So this is what we call it as the, if I write it here, it is VR1. So this is the basically what I call it as the velocity triangle at the inlet. The velocity triangle is a triangle drawn between the absolute velocity v1 is equal to absolute velocity at inlet. Similarly, what is u1? It is equal to the velocity of vane at inlet. And what is VR1? It is the relative velocity or effective velocity at inlet. So between these three, if you draw a triangle, that is what we call it as this is what we call it as. That means again I will draw in bigger things. So V1, VR1, right? So U1. So this is what we call it as the velocity triangle at inlet. Next, if I take the components of V1 in X and Y directions, so if I take what is the component of velocity, absolute velocity in X and Y direction, so this is the component of absolute velocity in X direction and it is in the called as Y direction. So what is VW1 and VF1? It are nothing but the components of absolute velocity in x, y directions, right? VW1 is called as velocity of whirl and VF1 is called as velocity of flow. The one means inlet. So this is another dimension. Now, the angle made by relative velocity with horizontal is theta. That means angle made by relative velocity with horizontal is equal to theta. This is called as angle of vane. Angle of vane means the angle made by relative velocity with respect to horizontal. And next, the angle made by the absolute velocity with horizontal is equal to alpha. This is called angle of jet. So how much terminology I have put it, you see, at the inlet, if I summarizing inlet velocity triangle, right? If I take inlet velocity triangle, so what I am drawing inlet velocity triangle, this is V1, right? This is U1, right? This is
what we call it as VR1. So if I write it as this is A, this is B, this is C. Now if I take the components of V1 in X and Y directions, this total is VW1 and this is VF1. And the angle made by relative velocity is called as theta, that is angle of the vane. Angle made by the absolute velocity is called alpha. This is called basically angle of jet. Alpha is angle of jet, but don't angle of jet, but remember angle made by v with respect to horizontal. Theta is the angle of vane. Angle made by VR with horizontal. Understood? So inlet velocity triangle. Now based on that, what is VR1? It can be very easy to draw it. Why we have drawn the velocity triangles? To calculate the relative velocity, we have drawn the velocity. Why velocity triangles? Why velocity triangle? To find the relative velocity. That is the basic thing. To find the relative velocity, velocity triangle is required. So that's why we have drawn the velocity triangle at the inlet. Similarly, we can draw the same velocity triangle at the outlet also. Suppose now I see the diagram once again. Number of times I am repeating is only for you to understand how I am doing it. So this is the vane, right? This is the x-axis. So now if I take it, this is the U. This angle is theta. This is how you should finally draw. This is V1. This angle is alpha. This is U1. This is horizontal component VW1. This is VF1. And this is VR1. This is theta. So once again, I will write it. Any way you write it. This is V1, U1. This is VR1. Horizontal component, vertical component. This is VW1. This is VF1. This is theta. This is alpha. So this completes as the inlet. But remember that this VR1 should be, if it is extended at the inlet, it should strike the horizontal at an angle theta. This is the thing you should draw. So that is the one thing. Similarly, now finally, the jet strikes the vane at a relative velocity VR1. So naturally, it should leave the vane at the same relative velocity. If I put it should leave the vane at like so. Naturally, it cannot be VR1, VR2 cannot be same because of the losses, and at the same time because of the unsymmetry of it. So it is actually VR2, right? So finally it strikes at a velocity VR1 and leaves at a velocity VR2. Then this is U2. U2 is also nothing but actually U only, but only to show inlet and outlet, the suffixes are shown. So this is what we call it as V2. So this is outlet velocity triangle. The outlet velocity triangle is such that if you see it, So it comes out with the relative velocity VR2 because finally it strikes only with VR with relative velocity. The same has to come out. So that's why the jet coming out is at relative velocity VR2 and the velocity of the vane is U2. And naturally, if you complete the triangle, that is what we call it as V2. Like in the last class, if you again draw the horizontal and vertical components of V2, so this is VW2 and this is VF2. So VW2 and VF2 are nothing but actually the horizontal and vertical components of this. So this completes it. Again, you remember the angle made by relative velocity with horizontal is phi because it is unsymmetrical. Otherwise, it should be theta, phi. Whereas V2 angle made by absolute velocity is beta. So at inlet it is alpha, at outlet it is beta. So this is what you should remember. And this VR2 should be actually the tangential. This angle is phi. So once again, I will draw outside when it comes actually it should be VR2 and it horizontal is U2, right? And this is V2. So this is exactly the velocity triangle. Now if I take angle made by this is phi, whereas here the horizontal and vertical components are VW2, VF2. This is beta. Phi is equal to angle of vane at outlet. Beta is equal to angle of jet at outlet. Right? Again, VW2, VF2 are components of V2 at outlet. Remember, if there are no losses, VR1 is equal to VR2. However, there will be losses. Hence, VR1, VR2 are different. VR2 is less than VR1. Similarly, if the plate is smooth, U1 is equal to U2 is equal to U. That is the thing. So these are the smooth VR2. Right? This is the starting point. So when we are deriving the equations, kindly remember this is the starting point. You know what is the now finally I will write inlet velocity triangle. Inlet velocity triangle V1, U1. You should extend, put it as theta. This is VR. VW1, VF1, alpha, theta. This is the inlet position. This is outlet velocity triangle. This is outlet position. So this angle is phi. So this is VR2, U2, V2, VW2, VF2. This angle is phi, this angle is beta. Right? This is the inlet outlet velocity triangles. Theta, phi are angles of vane at inlet outlet. Alpha, beta are angle of jet at inlet and outlet. VW1, VF1 are the horizontal component and vertical component of absolute velocity at inlet. VW2, VF2 are horizontal and vertical components of V2 at outlet. VR1, VR2 are the relative velocities at inlet outlet. Remember, this is angle of the vane means always this is with respect to VR. This is with respect to absolute velocity. These are with respect to absolute velocity. These are with respect to absolute velocity V1, V2. These are all relative velocities. So I completed this portion. Now straight away with this background, if you can write A, B, C at inlet. Similarly here at outlet B dash, right? Then actually VR2 means it is, if I can write ABC basically, so B dash, then we can write it as C dash, and this is basically A dash, right? And the remaining are, if you put this, for example, D, and here D dash, accordingly you can plan. So now I will go ahead with the derivation part. After successfully explaining the velocity triangles, now applying impulse momentum equation, we can derive the equation for force exerted by the jet. You already know the impulse momentum equation. So now straight away I'm going, what is the mass of liquid striking the vane per second is equal to rho A VR1, because it is relative velocity, only single vane. The next, applying impulse momentum equation, force exerted in the direction of motion is equal to Fx. Fx is equal to mass striking per second into initial velocity in x direction minus final velocity in yx direction. So what is the initial velocity in x direction? Initial velocity in x direction is equal to VR1 cos theta. This is the initial velocity in x direction. So now if I want to do it, I must write again the velocity triangle to make you to understand. So now what is the horizontal component of VR1? VR1 cos theta. That is what we have written. If I want to get what is this VR1 cos theta, this portion. VR1 cos theta means this small portion. This is the thing. So how can I get this portion? This portion total is how much actually? VW1 minus U1. If I put it, I am bound to get actually what is that? So therefore, it is equal to VW1 minus U1. So this is initial. What is the basically final velocity in x direction? Right. Similarly, I will draw the velocity triangle at outlet. So this is VR2. So this is U2. So this is V2. This is VW2. This is VF2. This is phi. This is beta. Right? If I take it again, a little bit confusion. So this is VR2. This is U2. This is V2. This portion is VW2. This portion is VF2. Angle made by relative velocity is phi. This is beta. So what is a thing minus VR2 cos phi? Am I right? Final velocity in x direction is equal to minus VR2 cos phi. What is minus VR2 cos phi? See, VR2 cos phi means what actually this is. This is the thing. So then what can I write for that? VR2 cos phi, it is equal to minus of U2 plus VW2. Right? This is final conclusion. So initial velocity in x direction is equal to finally what we mentioned VW1 minus U1. Final velocity in x direction is equal to minus of U2 plus VW2. Minus sign y minus indicates the velocity is in opposite direction. Therefore, Fx is equal to rho a VR1 into right VW1 minus U1 minus of U2 plus VW2. Right? So finally, what will happen if you see it? If I expand it, rho a VR1 into VW1 minus U1 minus plus basically. So plus U2 plus VW, right? then U1 is equal to U2. Therefore, Fx is equal to rho A VR1 into VW1 plus VW2. This is the expression. Here I want to make it clear. This equation is valid if beta is less than 90 degrees. If you can see the outlet velocity triangle VR2, U2, UV2. So this is the outlet tip. So this is VW2, VF2, this is phi, this is beta. So this is beta less than 90 degrees. For example, if beta is equal to 90, if I draw like this is VR2, V2, U2, beta is equal to 90 degrees. Okay, this is phi. So this case is beta is equal to 90. If beta is equal to 90 degrees, then what will happen actually? What will happen? Beta is equal to 90. You tell me actually. Then VW2 is equal to 0. There will be no horizontal component. VW2 is 0 and V2 is equal to VF2. So that is why in such a case, Fx is equal to rho A VR1 into VW1. So it is second case. This case is applicable, beta is equal to 90. Now beta is greater than 90. So that means again this is VR2. So this is U2. Now this is V2. This beta is greater than 90. Now if I take it V2 components, this is 5. This is VF2 and this is VW2, right? And VW2 will be in this direction. V2, VF2. So in such a case, actually, what will happen if beta is equal to greater than 90 degrees, then VW2 becomes negative. Therefore, Fx is equal to rho A VR1 into VW1 minus VW2 if it is beta greater than 90. So in all the cases, so therefore the general equation is Fx is equal to rho A VR1 into VW1 plus or minus VW2. So this is the most general application. Here beta is less than 90, then Fx is equal to rho A VR1 into VW1 plus VW2. And beta is equal to 90, then Fx is equal to rho A VR1 into VW1 and beta greater than 90 degrees, Fx is equal to rho A VR1 into VW. So these are the three cases. So with this, the force equation is complete. Then actually I will take up work done per second. is equal to Fx into U. So therefore, it is nothing but rho A VR1 into VW1 plus or minus VW2 into U. This is the next equation. Then normally, most of the cases, we will ask work done per second per unit weight of liquid. This is the general thing. So in such a case, it is equal to rho A VR1 into VW1 plus or minus VW2 into U divided by the weight of liquid. So in such a case, it is equal to rho A VR1 into VW1 plus or minus VW2 into U divided by, it is gamma into weight of liquid A into VR1, right? So gamma, you can replace it by rho G. Okay, rho, if you cancel it, rho can be cancelled, A can be cancelled. So naturally VR1 can be cancelled. So it will be 1 by G into VW1 plus or minus VW2 into U. This is called as work done per second per unit weight of liquid. This is the most common thing people will ask. So remember, it is 1 by basically G into VW1 plus or minus VW2 into U. So this is the case. So in conclusion, what we have learned in this lecture is number one is how to draw velocity triangles. What for velocity triangles? How to draw velocity triangles to calculate the relative velocity. Then second one is calculation of Fx. Third one is Fx for beta less than 90, beta is equal to 90, beta greater than 90. Then once that is over, work done per second. And last point is work done per second per unit weight of liquid. So these are the cases which we have studied. All these cases are basically what for we have studied all these cases. Remember it, it is a single unsymmetrical vane moving jet striking at one tip. So this is the thing. So here I will stop this lecture, and next class we will go into another lecture. So for any of the future things, the basic crux of this whole thing lies at which point is how you can really do the how you can really do with the calculation of the what you call it as an unsymmetrical vein jet striking at one end.
Like, share, and subscribe. Hit the bell icon for more updates.